All right, this is example 1818. Okay, we are given source voltage, 50 volts, and of course that is 50 volts what? Peak to peak, peak or RMS? You have three choices.
Peak.
What?
Peak to peak.
Really?
No. It's RMS.
There it is.
No.
RMS.
Yeah.
Okay, so what would that actually be if we wanted to look at that voltage as a standard voltage definition in waveform or in sine form? That would be what? 50 times 1.414, which gives you the peak value, right? Sine omega t, and in this case plus 0 degrees. Because remember, when we use that form, it's always in peak. And when we use the form where we give the angle like this, it's always given in RMS. And the reason for that is because this number is used to predict in a waveform, or that equation is used to predict in a waveform where you will be in that waveform after a certain amount of time has gone by. And in order to do that, we have to be able to access the peak value because there will be a time it will be at that voltage. So when we talk about the waveform, we're talking about a peak value. When we talk about it as a source of energy into a circuit, then we're talking about an average value. It's as simple as that. Okay? So given that, we've got an RMS value for voltage. They've gone ahead and graciously labeled what they're going to think the currents are going to do. And it seems to make sense since it's the only source in here. We can kind of draw our currents this way, and they will recombine down here to make the source current. Okay? We also have a resistor and a inductor in series. They've been gracious enough to give us the reactance instead of making us calculate that based on some frequency or omega value. And they've done the same thing here. Here's our capacitive reactance. And what our job is to do is to determine the entire circuit's impedance. Okay? So that's the first order of business today, is to determine what the impedance is. Then, from that, we will determine what the currents are, and then we will determine what the currents through each component are, and then we'll look lastly at the power consumption or dissipation for each one of these. Sound good?
Sounds frightening.
Frightening. Well, it is that time of the year. It's Halloween, right? Okay, so let's go ahead and start out by creating blocks in this drawing. We're going to put one block here, and we're going to call that the impedance, Z1, is equal to 1K plus J0, because there is no reactance in that component. This block, because they're in series, we can simply add them together. That gives us 1K plus J, and it's plus J because we're looking at an inductor, 2K. And this little feller over here is minus J, 2K, because he's a capacitor. He's in the downward direction. His reactance is in the downward direction. So we use a minus J to indicate it's 180 degrees away from the plus J we have here. Okay? So let's redraw that. 50 at an angle is 0. This is, what did we say? 1K plus J0. This is 1K plus J2K. And this is minus J2K. Okay, if we go ahead and just draw this here, this here, like this, we should be able to pretty much turn off our display, and there we are. Okay, so from here on out, we can concentrate on this drawing. It says the same exact thing that we had before. We've just put it in a different form. And moved it back over to the middle of the board, which is always a good thing. And that, of course, is 50 at an angle of 0. Okay, are we ready to jump into figuring out what the total circuit impedance is going to be?
Yep.
Let's call this Z1. Let's call this Z2. And we'll call this Z3. And what I'm going to say is that the total impedance is going to be equal to Z1 plus Z2 in parallel with Z3. How do we feel about that? Does that look about right?
Yep.
Z1 plus Z2 in parallel with Z3. All right, so the hardest part of this, of course, is going to be to figure out what Z2 in parallel with Z3 is. So let's do that first. We always like to do the hard part first. Z2 in parallel with Z3 is going to be 1 over Z2 plus 1 over Z3. Look familiar? Of course it does. It's our old friend, the parallel formula, modified slightly to accommodate the fact that we're talking about impedance. Okay? Okay, what is Z1? Since we're going to do division, at least it smells like we're going to do division, doesn't it? We might as well take the opportunity to take a step back and write down what these are in polar coordinates, since we always divide and multiply in polar. 1K plus J0 is going to be what? 1K at an angle of 0 degrees. This one will be equally as simple. It will be 2K at an angle of minus 90 degrees. This one, however, you're going to have to punch some numbers in your calculator to get the answer, unless you're a lot smarter than I am, in which case I'm going to take it up. You know, one of the things that we do here, we don't dick around with these numbers like 1,000. Just for everything's in K, so just forget about it and add the K at the end. Okay, so let's just look at this as 1 and 2, and then we'll add the K at the end. So I'll take 1, second function xy, 2, second function rectangular to polar, and I get 2.23. Actually, we'll make it 2.24 just to be accurate, and then we end up with an angle of 63 degrees. And now we put back the K. I don't like working with the big ass numbers. If I can make it simpler, I'm going to do that. That's what engineers and technicians do. Okay, so now we have Z2 is 2.24 at an angle of 63 degrees, and Z3 is 2K at an angle of minus 90 degrees. And before I forget, I forgot to put the K there. 2.24K at an angle of 63 degrees. 1 over 2K at an angle of minus degrees. We assume at this point, of course, like we've done before, that if there is no angle, the angle is equal to 0. And we need to have a number because we're going to do a little subtraction. Okay, so this guy right here, let's not forget, eventually we're going to have to do this divide into one thing. But for now, let's look at this guy here and let's look at him. This guy here is going to be 1 over 2240 at an angle of 0 minus 63 degrees. That's the math that we're going to do to get there. This one is going to be 1 over 2000 at an angle of, careful, 0 minus negative 90 degrees. When we divide the coefficients, we do subtract the angles. Okay? What's 1 over 2240?
446.
How much?
446.
No, it can't be. 446, it can't be. It's got to be a number that's less than 1, certainly.
Point 446.
0.446. And 0 minus 63 is?
Negative 63.
Negative 63. Okay?
I'm not coming up with that .446. I'm coming up with .000446.
Are you?
Did you put the K in there?
I don't know. You guys need to come up with the right answer. I had here
Okay.
1 over 2,240. How that can be close to a half, I don't know, but I'm going to let you guys write down any wrong answers you give me for first quarter stuff. So let's try that again.
I got .446 milli,
Or
or .000446.
446 micro. Right?
Yeah.
And this one, I know 1/2 is 0.5. So if it's 1/2 is 0.5, then it's going to be 0.05, 0.005, 0.0005. Correct? So this is going to be what? 500 micro at an angle of 0 minus negative 90, which is the same as plus. So that means we have 90 degrees here.
Sounds like what? Like minus negative 90.
Minus negative 90 is plus 90. Yes.
He got me, man.
Okay. Any objections to these numbers? Don?
No, then we still need to do 1 over, right?
Yeah, well, we've got two things to do. We're screwed big time because not only do we have to do the 1 over, but we do that after we add these together, which means we have to convert both of these back to rectangular, add them together, and then convert it back to polar, and then divide it into 1. So, you know, we can bitch about it all we want, but we might as well just do it. Okay, so
You can cry about it too.
we need now to convert this to rectangular. 446 micro at an angle of minus 63. .446 micro. I'm a little old-fashioned. .000
You can't tell.
446. Second function x to the minus y, and we have minus 63 degrees. Second function polar to rectangular gives us 202 microamps, or a micro. It's not amps.
J445.
What is it?
J445.
It's minus though, right?
Yeah, negative
Minus J,
445.
I have 397.
I've got 397 too,
Really?
micro.
Micro.
You're gonna have to try that again.
Negative 65.
What did you get? You could be the tie maker here.
Never mind.
Did you figure out what you did wrong?
Yeah, I typed it wrong.
You fornicated against the force of gravity.
Ah!
All right, what about this one?
It's bound to happen.
500 micro at 90.
Bound to happen. Can't deny that.
500 at 90.
Negative
Are you
5.
figuring that out?
Negative 5 micro J.
1.5 million.
You guys are so funny. You guys are so funny. If it's at an angle of 90 degrees, that means it's just J 500 micro, isn't it?
Yep.
Mm-hmm.
Yeah.
That's what I
You
said.
guys go right to the calculator without even looking at the damn numbers. Shame, shame, shame.
It's a bad habit.
Okay, so we now have these. And we have to add them together. Remember, don't forget about this little plus sign up here. First thing we did was we did the division. We came up with the answers for the division, then we converted them over to rectangular coordinates so we can add them together. Once we get them added together, we still have to divide them into 1. Yeah, aren't we lucky?
Yeah.
Okay, so we have 202 micro minus J 397 micro plus J 500 micro. That's going to give me 202 micro plus J 103 micro, if my calculations are correct. 500 minus 397, last time I checked was 103. So we should be in good shape. Okay, so we are sitting here right now trying to calculate Z2 in parallel with Z3, and we are now at this point. And this, of course, is 1 at an angle of 0. We need to get this again. Convert again. Back to polar. (202). Second function, 103. Second function, rectangular to polar.
Yowzers.
I did something wrong.
226 micro at an angle of 27 degrees.
What is it?
226 micro at an angle of 27 degrees.
I'll have to buy that for $1.
Anybody disagree with that number? Does that look right? What about you? What'd you get?
I'll buy it for $1.
Okay, you're gonna coattail on this one?
I'll buy it for $1.
Okay, so this is the same as that, isn't it? These two the same thing?
Yeah.
So I can replace this with that. 226 micro at an angle of 20, is it 27 degrees positive?
Yep.
Yeah.
Okay. 1 over 226 micro at an angle of 0 minus 27 degrees. That's the math we do. We divide the coefficients, subtract the angles. So 1 over 226 micro that's a pretty juicy sized number.
Yeah.
4.42K.
How many?
4.42K.
At an angle of
27.
Negative 27.
negative 27. You and those negative signs.
Oh, it's 0 minus 27.
It certainly is.
Yeah, okay.
It certainly is. Okay, so what do we get here? What is that? We went down this road and we forgot where we started. What were we
That's
trying to
just
calculate?
Z2 in parallel with Z3.
That's just Z2 in parallel with Z3, right? What is the total Z going to be?
So you gotta add the 1K at an angle of 0 to that after you convert it to rectangular.
1K at an angle of 0 degrees, which is our resistance of Z1. And then we're going to add to that what we just got done calculating, which was 4.42K at an angle of, what was it, 27 degrees negative?
Mm-hmm.
Okay, so ZT is going to be equal to 1K plus J0 plus this, which was equal to 4.42K at an angle of minus 27 degrees. And unfortunately, we now again have to convert this over to Cartesian coordinates so that we can add. Okay, so 4.42K at an angle of negative 27 degrees should give us 3.93K plus J2K. Is that what you got? And then we're going to add to that
Is it
1K plus J0.
Is that a negative 2?
Yeah, I think that should be a negative.
That's what I was just redoing my
But you didn't ask.
calculations, 'cause I
You
thought
should
it
have
was.
asked. You should have asked, Don.
I just redid my calculations to be on the safe side.
Bad boy, Don, bad boy.
Okay, so when we add all this crap together, what do we get? We get 5K minus J2K. Right? 4.93 as far as I'm concerned is 5K. Not going to squabble about that. So that is our total impedance. After all that, that's all we figured out.
And convert that back to polar.
What's that?
And convert that back to polar.
Why would we want to do that?
I don't know. I don't know, that's what we've been doing.
We might end up having to, who knows? Probably not though, since we don't have to add or subtract that to anything. But we will have to go back to polar because what we're going to have to calculate is the total current. What's the total current equal to? IT is equal to what? Ohm's law says it's equal to V over R. But in our little microcosm here,
V over Z.
V over ZT, which is going to be 50 at an angle of 0 degrees, divided by what you said, which is we're going to have to convert this back to polar notation, right? We change it over to rectangular to add the stupid 1K in. Once we got that done, that gave us this. Now we have to convert it back because we need to divide.
So it's 5.3K degree negative 22.
Is that what you all got? 5.3K at an angle of minus 22 degrees. And the answer to that then is going to be 50 over 5.3K at an angle of 0 minus negative 22 degrees. Here we go with the double negative again. All right, 50 over 5,000 is 0.01, so I'm going to say it's about 0.009. Maybe.
Yeah.
Yeah.
Because it was 50 over 5,000, it would be 0.01
Degree 22.
at an angle of 22 degrees. So our current, total current, is equal to 10 milliamps at an angle of 22 degrees. Okay?
And then we convert that back to.
Convert that back to rectangular.
Are we good? Holy moly, it's with 25 minutes and we're not even halfway done. How do you feel about